Okay, let's talk a little bit more about limit points and closure. So first, let's recall the definition of what a limit point is. The set of limit points of a set E is all the points, say X, in the overlying metric space. So E is a subset of X, a metric space. It's all the points X which have every neighborhood of that X intersecting E, sort of non-trivially. Sort of not just at X. So picture, say this is E and this is X. If I've got a point here, it's going to be a limit point because no matter which circle I draw, which neighborhood I take, part of that circle here is inside of E. Right. That's what makes that point X a limit point. Since all the neighborhoods meet E. Okay. So why do we call these things limit points? Limits that we've sort of traditionally heard of deal with sequences. You take a sequence and the limit of the sequence is some number. Why are these things called limit points? Well, we don't quite have the definition of sequence yet, but let's write down a theorem which is true, and we'll prove it, and we'll kind of see why this is our definition for a limit point. So, theorem. If X is in E, it doesn't have to be in E. If X just is a limit point of E, which is a subset of X, a metric space. So we'll make it a metric space by adding a distance function next to it. So if X is a limit point of E, which is a subset of a metric space, then there is a sequence x1, x2, dot dot dot, all of which the xi's are inside of E, and for any epsilon bigger than 0, there exists n in the natural numbers such that if I is bigger than n, xi is in the neighborhood of size epsilon around X. Okay, so what does that say? That's a lot of math right there. So let's kind of draw a picture to go with this. So I've got this point X, and it's the limit. It's a limit point of this set E. We don't really know what this set looks like, but we'll call this E. E's the stuff inside there. I can find a sequence x1 in here, x2, x3, x4, and so on. And these are just going to keep getting closer and closer to x. I mean, x3 might be closer than x2 is, x2 might be closer than x3 is, I don't know, but what eventually happens is if I'm given any epsilon, if I draw an epsilon neighborhood around x, I can go far enough out in the sequence. If I go out to n in the sequence, xi is in this circle if I is bigger than n. So the entire tail of that sequence is in here. Right. And if I make the circle smaller, I can go farther out in the sequence, and the sequence is in that smaller circle. So the sequence eventually just kind of fits into these tiny, tiny circles around x. That's what kind of makes it the limit point. Okay, let's prove that this theorem works for us. So here's our proof. So we need let x be a limit point of E. We need to construct a sequence inside of E that satisfies this conclusion, right? So what we're going to do is we're going to start out with big circles. I'm going to draw a real big circle around x, and I know that this big circle intersects E, so I'm going to take something inside that big circle and also inside of E, and we'll call that x1. Then what we'll do is we'll take a slightly smaller circle. We'll take something inside of E that's in that slightly smaller circle and call it x2. Because x is a limit point, no matter how big of a circle I get, I can always find something inside of E inside that circle, so we'll just keep doing this. Take another slightly smaller circle, find something in E that's in that slightly smaller circle, call it x3, and repeat that process. These circles are sort of concentric, they're all centered at x, so these circles are shrinking down, and the limit points, or the points in the sequence, just keep getting closer and closer to x. That's going to be our sequence. Okay, so let's actually write down mathematically what's going on. Okay, so we have a limit point of E. Since x is a limit point, if I'll use delta because epsilon is sort of given to us in the statement of the theorem. So if delta is bigger than 0, by being a limit point, the neighborhood of size delta around x intersected with E is not equal to the empty set. So there's stuff inside this intersection, right? Let's take stuff inside that intersection. Okay. We'll create x1 by saying x1 is in the neighborhood of radius 1 around x. So let's let x1 be in there. Let's let x2 be in the neighborhood of 1/2 around x. So we're going to make these circles smaller as we go farther out in the sequence. x3 is in the neighborhood of 1/3 about x. So on, let xi, that's going to be in the neighborhood 1/i around x. Okay. This sequence satisfies the theorem. Because given epsilon bigger than 0, there is an n in the natural numbers with n times epsilon bigger than 1. That's our Archimedean property. So epsilon is bigger than 1/n. if we take any I bigger than n, then 1 over I is less than 1 over n is less than epsilon. So, by construction, x sub I being inside the neighborhood of 1 over I of x is a subset of the neighborhood of epsilon of x. I was arbitrary, so as long as I is bigger than n, this works. That's our proof of that little theorem. So any limit point in a set, we can come up with a sequence also inside that set that approaches that limit point. Okay. We don't have sort of a formal definition of what it means for a sequence to converge yet, but this is going to be kind of how we're going to define what we mean by a sequence converging. Okay. Let's look at some closed sets now and see what it means by closure and how we close a set if it's not closed. So a set is closed if it contains all of its limit points. Right. Well, let's get some notation. We'll say E prime, it's the set of limit points of E. And we'll just say it's x in x such that x is a limit point of E. And our definition of limit points we had just gone through, it means that any circle around that point intersects E, not just at x. And another thing we're going to have is going to be E bar. E bar is E unioned with its limit points. So we're going to add the limit points to E and make it a slightly bigger set. We'll call it E bar. We'll call this the closure of E. So the closure sort of as a name implies that it's closed. Well, we've got to prove that. I mean, I've taken all the limit points of E and I've added stuff to them, right? How do we know for sure that adding more points didn't cause us to find more limit points then? I've added more points, that gives us more opportunities. It made the set bigger. Did I sort of include more sequences that approach things that are outside this new bigger set now? Well, the answer is no. And let's prove that. That's this next theorem. It's theorem 2.27 in your text. So it's got 3 parts to it. E closure is closed, which is good. If we're going to call it the closure of something, it should probably be closed. The second part is E is equal to its closure if and only if E is closed. So if I already contain all my limit points, adding limit points to me doesn't change anything, right? This one's sort of a really easy part to that proof. And then C, E closure is contained in F for every closed set F which contains E. So there's an overlying metric space, sort of everything. E is a subset of X and F is a subset of X. where X is a metric space. That's kind of assumed. I didn't write that out, but that's kind of our idea all the time. So let's prove this. So we need to show something's closed, right? Well, we have the theorem that its complement is open, right? A set is closed if and only if its complement is open. So let's use that. Let X not be in E closure. So X is not in E union E prime, right? So there is a neighborhood of X that does not intersect E. Why is that? It's because if every neighborhood intersected E, then X would be in E prime, right? But that's not quite true. I mean, it could be an isolated point of E, but we took away E2, so X can't be an isolated point and it can't be a limit point. So there has to be some neighborhood of X that doesn't intersect E at all, even at X itself. Doesn't intersect outside of X because it's not a limit point. Doesn't intersect at X because it's not in E. This makes X an interior point of E bar complement, since this is true for all X in E bar complement. E bar complement is open, making E bar closed. Okay, so kind of the picture. Right. If this is E, we included the boundary. And this is E union E prime, which is E closure. What we did was we showed the set out here is open. Since any point out here, I can draw a circle around it that stays away from E bar. Okay. Let's prove the second part now. B. We want to show that E equals E bar. If and only if E is closed. Okay. So let's go this way first. So if E equals E bar, then E equals E union its limit points. So E prime must be a subset of E, making E closed. If a set contains all of its limit points, it's closed. Okay. And then the other direction, if E is closed, then E prime is a subset of E, so E union E prime equals E, which is what the statement says, right? So that checks B off. Then the last part, we get the smallest closed set part. So E bar is a subset of F for every F. Oops, for every F containing E that's closed. Okay. And so if F is closed and F contains E, the closure of E is contained in F. Okay. So if F is closed, then F contains F prime, right? Its limit points. Since F is bigger than E, F prime contains E prime. Right? So F contains E union E prime as F is closed. We sort of get this final inequality. F contains F prime contains E prime, and F contains E. These things together show me that. Okay. So this says E closure is the smallest closed subset of X containing E, because any other closed subset has to contain it. So we can kind of generate what the closure is by looking at closed subsets and making them as small as possible, taking the intersection of all the closed sets. So sort of another remark. E closure is equal to the intersection of F containing E, F closed. If I take the intersection of all the closed sets that contain E, you get the closure. So let's look at just a real quick example on the number line of what the closure is. Sort of a silly example. Say I'm looking at the open interval from 1 to 2. What's the closure of that? Well, it's the smallest closed subset that contains that. So here's a closed subset that contains it, but it's not the smallest one, because I could take 1/2, 5/2 instead of 0, 3. Right? The smallest one that contains it is going to be the closed subset 1, 2. This is the closure of 1, 2.